In the coming lessons, we're going to be introducing some more realism and building out our intuition for the machine learning problems that are to come. We're now going to have a look on how you'd run a gradient descent algorithm given some data points and using a real cost function. This cost function is called the mean squared error, or MSE. Previously, we've been using example cost functions to learn more about how our gradient descent algorithm behaves. And this was fine at the time, but now we turn our attention to a cost function that is actually being used in practice for many machine learning problems. Now, to recap a little bit about linear regression. We said that the goal of linear regression was to minimize the distances between the points and the line. And a good line was one that minimizes the residual sum of squares. When we were talking about the distances, we meant the distances between the data points, so the actual values, the y's, and our fitted values, or our hypothesis. To calculate our residual sum of squares, we took the difference between the actual value and our fitted value, and then we added them all together. But because some values would have been below the line, adding them all up just like this would create a problem. So what we have to do instead is we have to square all the values and then add them up. Thus, our goal was to choose a line or choose the parameters, theta 0 and theta 1, that would minimize the sum of the squared differences. And the name for this equation was the residual sum of squares, or RSS. The way to interpret this number, this residual sum of squares, was as follows. It's how much of the dependent variable's variation our model did not explain. So it's the sum of the square differences between the actual y values and the predicted y values, and the smaller this residual sum of squares, the better our model fits our data. And the greater the residual sum of squares, the poorer our model fits our data. Thinking about it this way, what would be a perfect fit? What kind of model would have a perfect prediction? Well, it would be one where the residual sum of squares is 0, right? A value of 0 for the residual sum of squares would imply a perfect fit. So I know that at this point, you're probably thinking, would the residual sum of squares make a good cost function? And the answer is, yes, it would, but with one small modification. And that modification is dividing the whole thing by the number of data points. Then the residual sum of squares gets a new name, and this equation is called the mean squared error, or MSE. And that's the cost function we're going to be using in our last example. Back in our Jupyter notebook, let's add some section headings. So I'm going to change my cell to markdown here, and I'm going to put in £1 symbol, and then I'm going to write example 5. Working with data and a real cost function. And below that, I'm going to add a subheading that reads mean squared error, colon, a cost function for regression problems. This is also a really good opportunity to try our hand at writing some more LaTeX notation in Jupyter. Let's add the formula for the residual sum of squares first. I'm going to make this fairly large, so I'm going to give it 3 pound symbols, $2 signs, RSS is equal to, and now we need that summation symbol, and that's going to be with the sum tag. That's how we're going to get that summation symbol. Let me add another $2 signs as the closing tag. Hit Shift Enter and show you what I mean. So backslash sum gives us the summation symbol. Now we need to add some things to the top and the bottom of the summation symbol. I can add things to the bottom with the underscore, and there inside some curly braces, I'm going to write I equals 1, and then I'm going to use the carry symbol and another pair of curly braces, and put an n to put something on top. Let me hit Shift Enter and show you what this looks like. Now I'm going to add the rest of the equation in some big parentheses. So I'm going to hit backslash and then write big for the big tag, open parentheses, and then space, another backslash, big, closing parentheses. And then everything inside the parentheses will be raised to the power of 2. So I'm going to say carré and then 2. Let's take a look at what this looks like now. All right, so now I'm just going to add the final bit. And that's going to be y to the power of curly braces, parentheses, I. So it's going to be the ith value of y minus h underscore backslash then theta for the Greek symbol, space x carré curly braces parentheses I for the ith value of x. I'm going to put another space here at the end to make it a bit more readable and hit Shift Enter and take a look at this equation. Okay, so I think that looks pretty solid. And in the process, we've discovered a few more LaTeX tricks. One is that this underscore adds things to the bottom, like this I equals 1 for the summation symbol, or the Greek letter theta for our hypothesis for h. And we also see the big parentheses in action with the big tag. Now, adding the LaTeX equation for the mean squared error is actually going to be very easy, because I'm just going to copy this and paste it, and I'm going to modify it. So instead of RSS, it's going to read MSE, and then just in front, I'm going to add a fraction. So I'm going to add backslash FRAC, a pair of curly braces, and then 1, and then another pair of curly braces, and then n. And when I hit Shift Enter, I can now see my mean squared error equation like so. Now, one thing I'll point out is that you might see an alternative way of writing this equation. Sometimes this equation is written with a y hat, with a little carré symbol above the y, instead of this notation with the hypothesis function, instead of this h theta xi. So let's add the alternative notation as well so that we've got it on here. So I'm going to select this part here, which reads h underscore backslash theta xi. I'm going to delete it, and instead I'm going to show you guys another LaTeX tag, which is backslash hat, followed by a pair of curly braces and a y inside. When you hit Shift Enter now, you should see this. The other thing I'll do is I'll remove the carré, the curly braces, and the I from the preceding y value. So I'm going to delete that and hit Shift Enter, and let's see what this looks like. So these are the two notations that you're going to come across most often. The predicted value is either represented as the hypothesis function, so using this h notation, or it's represented with this y hat notation. This is also very, very common. And y hat is also going to be the way I'm going to be referring to our predicted values in our Python code that we're going to write. Now, with the notation out of the way and just looking at these equations, you probably might be wondering, why is the mean squared error more useful as a cost function than the residual sum of squares? I mean, they look pretty similar, right? But let's think about it. What would happen when our data set gets large? We're going to have a y and a y hat value for each and every data point, right? So as we're adding more and more data points to our data set, that sum starts to get pretty big because we're adding up all the square differences, right? And we've already seen what happens when computers are confronted with very, very large numbers before. That's right. When working with very, very large numbers, we might encounter our old friend, the overflow error. And this is where the mean squared error comes to the rescue. Because what happens when we're dividing by the number of samples? by dividing that sum by the number of data points, we're kind of taking an average, right? An average, a mean. So hence the name, mean squared error. And dividing by that number of samples, you can start to handle very large data sets, right? Data sets with tens of thousands of data points. And the cost function isn't going to encounter an overflow error because you're keeping that mean squared error manageably small. So I hope that explains why the mean squared error is a very, very popular cost function, because it allows people to handle data sets of all sorts of sizes. And your gradient descent algorithm won't cause an overflow as you're scaling up.